This begins CS 402X with Professor Cheng on Monday, July 21st, 2014.
All right, let's get started. Kernel 3 is due in less than 2 weeks, due on Thursday, July 31st. And again, if you have code from previous semester, don't copy from it, best to get rid of it. And grading guidelines is the only way we will grade, and after submission, make sure you verify your submission. Okay, so Kernel 3 is still the same. Every branch of the code must have at least one DPG statement, and please use the required format. Grading 3, S is a section, A, B, C, D, E, F or something. X and Y may be optional, depends on how you organize your README file. If it matches what's in the grading guidelines, then use the X and Y, but otherwise, depends on what you do in your README file. Okay, and please, and I still see that people haven't read the Kernel 3 spec, okay, so make sure you read that. Read the Kernel 3, not the spec, the FAQ. There's a lot of stuff to read, but, make sure you read it first. Read the spec and read the hints. And again, I will add more stuff as appropriate. Okay, so we only have 4 lectures left. There are 2 this week, 2 next week, and then the final exam is on Monday of the last, the last week. And so even though this is not going to be related to the kernel assignments anymore, but still these are very, very important operating system concepts. Okay, if you want to get a job in industry, any kind of a system-related, stuff, you sort of need to know how the operating system works. Okay, so still important topics. All right, so last time we were almost finished with the backing store. I guess I went ahead and modified a couple of these slides, so I'm gonna, start from here again, talking about the backing store. Okay, so this slide is still the same as before. All I added was the last sentence over here. Is that Unix support this type of backing store. Right? So this type of backing store, number ones, are the read-only pages. So they don't really need a backing store because you already have a file object pointing to where that page came from. The second type is that when you call memory map to map a file into the address space, if these files are shared, then whenever you write stuff to it, then they go to the disk. So again, the file object will tell you, where the backing store is. So you don't need explicit backing store. Okay? The other type is where you need to explicitly manage a backing store, and Unix doesn't support that, but we still need to sort of talk about in the regular operating system what needs to be done. Okay, so this includes 2 types. One is the read-write private mapping of a file. Okay, so this includes things like data section, of executable. Whenever you try to do modify those data, then you're using copy on write. So therefore, the modified pages needs a backing store. If you have a privately mapped file, and again, if you modify to it, then you need a backing store. Okay, so in this case, the pages came from the file, but the modified pages associated with their associated shadow objects must be backed up into the swap space or the backing store. Okay, the third one is the anonymous memory. So these things came from pages that are initially filled with zeros. So for example, the BSS, the stack. And the heap and all that kind of stuff. So these pages are created zero-filled on demand. Okay, so in the beginning, when you start with that, you get a page of 0. And anytime you modify it, of course, after you modify it, then they have to be have a backing store. Okay, so the modified pages of these with their associated shadow objects must be backed up in the swap space or the backing store. All right. So the space that corresponds to these backing store, I guess there's a question of when do you allocate the space on disk to store these objects? Okay. There are basically two approaches. One is, and somewhere in between, one is the radically conservative approach. Okay, so this is falls in the category of eager evaluation, which is the opposite of lazy evaluation, and the other approach is the lazy evaluation approach, and this is the radically liberal approach. Okay, so the lazy evaluation is to say that when you need a backing store, well, you don't really allocate that on the disk until the very last possible minute. And what is the very last possible minute to allocate stuff on the disk? Well, it's whenever you're ready to swap out that page of data onto the disk. Okay, so you basically just point to the disk and says, well, I need space later on. Right now, I don't need to allocate that on disk. When that object needs to be swapped to the disk, that's when you do the allocation. So you delay that to be as late as possible. So that's lazy evaluation. Okay, and the problem with the lazy evaluation is that when this happens, when you try to swap the data onto the disk, what if there's no disk space? Okay, you're doing allocation on the disk. At that point, the disk is completely used. Okay, and then this page needs to be swapped to the disk. Okay, so what do? I guess you crash. Okay, so it's really not a sort of a desirable effect. Okay, but the idea over here again is that you won't waste space on the disk because you delay the allocation of the disk to be as late as possible. So maybe this process it's going to get killed before it needs to swap to the disk. So therefore you save space on the disk, and you also save time allocating that ahead of time. Okay. On the flip side of this is this radically conservative approach doing eager evaluation. Okay. Whenever you create these objects that's supposed to have a backing store, that's when you do the allocation on the disk to have the backing store. All right. So in that case, what happens is that when you try to create, a page of memory, okay, and if at that time you don't have any space in disk, you don't have any space on disk, that's when you fail. Okay, so when do you allocate such a page? All right, so we have seen that when you call malloc in user space, okay, you might end up starting to do stuff modifying pages and end up to modify a copy on write page. At that point, if you go to the disk and you say, hey, allocate a page for me, and the disk says I have no room. Okay, so therefore, malloc can actually fail when you haven't run out of virtual memory. Okay, so that's why when you even write user program, when you call malloc, you should always check the return code, just in case the return code says I have no more memory. What it's because the swap space is full. Okay, so if you're using the eager evaluation approach, when you call malloc, you can actually run out of disk space. Okay, so in that case, I mean, the effect is a little more, sort of a predictable, and you can handle it programmatically, because when you call malloc, you check the return code. If the return code is null, then you know that you run out of disk space. Okay, or it's possible you run out of virtual address space. That's another possibility. But most likely is that you run out of swap space. Okay, so at the time when you try to allocate that disk space, that's when you fail. So it's easier to handle it programmatically. If you do the lazy evaluation, then this is the time when the operating system decides to swap out that page onto the disk. So it could be at a random time, and all of a sudden your user process get killed. Okay, so even though this is more efficient to do lazy evaluation, but your process may get killed at a really bad time. All right, so again, there's a trade-off between these two. And there's some system, out there like Windows try to do somewhere in between. So when you trying to create an object that needs a backing store, some space on the disk is reserved to say that, hey, I know that I need this much disk space on the disk. Okay, but you don't really allocate that space telling you where it is. Okay, and later on when you're ready to write that disk page onto the disk, that's when you actually do the allocation on the disk to commit a certain part of the disk to store that particular object. Okay, so it's a mix of two. And that's what Windows does. Linux in general, or Unix system, they tend to do the more conservative approach. So on Solaris, when you call malloc, you will notice once in a while when the Solaris, when the load is really, really high, when you have tons of processes running on Solaris and they all use up a lot of swap space, your malloc can pay. All right. So again, different approaches. These pages X out. All right. And I guess we sort of talked about some of these stuff already, that in kernel 3 you need to look at PT and netcode to understand how the page table is allocated. Okay, so this sort of ends chapter 7. Let me go back here. So the plan right now is that we finish chapter 7, okay? And if you look at the lecture webpage, there's a lot of stuff that says, we'll finish this first after chapter 7, second, third, and then 4, 5, and then 6, and then finally 7. Okay, so these are, what I'm trying to cover during the last 2 weeks. So we're going to start with this first, and then we're going to jump to chapter 4, and then we're going to jump to chapter 5. All right? Some of these topics are, again, very important, virtual machines, scheduling, and all the file system stuff. These are all part of the coverage of the final exam. Okay. All right, so we're going to go back to chapter 6. We finished the first part, giving you sort of an overview of what the actual file system looked like, and then we're going to talk about some of the issue with the actual file system. All right, the first thing that we're going to talk about is how to deal with crashes. Okay, towards the end of the first time we talked about chapter 6, we sort of mentioned that there's this approach called the buffer cache. Okay, and buffer cache is the modern way of the operating system dealing with the inefficiency of disk. You want to basically make sure that when you try to read the disk, you read at full speed, and the way you do it is to use a buffer cache. Use lots and lots of memory so that when you try to read some data on the disk, well, the data is already in memory. So basically, you never go to the disk when you're asking for a piece of data. Most of the time, it's going to be there. Okay. The problem with the buffer cache is that what happened with write. Okay. If you have a buffer cache, in this picture, we show a buffer cache. The read will basically, all the read operation will hit the cache. You have a cache hit. So you don't have to go to the disk, okay? So basically all the read operation, the data just return right away, okay? Once in a while you have to go to the disk, okay? But when you do the write operations, you write to the buffer cache, okay? So the data really doesn't go on the disk, okay? So this picture shows you these pink regions. These are the dirty blocks, right? The dirty blocks are the blocks that have been modified. So therefore these blocks, if you look at what's on the disk, is that they will be different. Okay, so that's why these blocks are called dirty. They don't match what's on the disk. If the block match exactly what's on the disk, then these blocks are called clean. Okay, so these dirty blocks, when do you write out these dirty blocks? Well, you can write it out right away, but what you normally do is that you have a scheduler try to schedule these things to write to the disk. Okay, so maybe you write this one first, followed by this one next, and followed by the other one. And remember that lots of processes are modifying these buffer cache all in parallel. Okay, so there's going to be a lot of blocks that are getting dirty, so they all have to somehow sequentially go to the disk if there's only a single disk. Okay, so it can actually take a while before these data go onto the disk. Okay, so what if you get a crash, you lose power, somewhere in the middle of writing out the disk? Okay, then what happens is that something is going to become inconsistent, right? Because as far as your application is concerned, or as far as your operating system is concerned, this is sort of the world, of the system. Right, that this, the view of the application look at the disk is that this is the disk. The buffer cache is a disk. Because when you read and write to the disk, you actually only read and write from the buffer cache. Okay, so the application thinks that this should be the view of what the disk is supposed to look like. Okay, but in reality, because these delay writes, what's on the disk is not the same as what's in memory. Okay, so therefore, if you lose power or if you have an operating system crash, when you get an operating system panic, then none of these blocks get written out to disk because you have a halt in the kernel. Okay, so therefore, what's on the disk is not going to look like this. Okay, is that okay? Well, it depends. Okay, depends on what's not inconsistent. All right, so things over here, may become inconsistent, but some of the inconsistencies are not so bad. Some of the inconsistencies are really bad. Right, so if you go back to what the inode looked like, in the inode, there's a disk map. The disk map points to a bunch of blocks. What if the inode is messed up? What if the disk map is messed up? Well, then the memory location. Right? Remember the disk map in the system file system is 13 pointers. Okay, if the pointers are pointed to the wrong location, it's almost like a segmentation fault. right? So next time when you try to open this file, it's going to point all over the place. You're going to end up getting bad data. All right, so we don't really want inode to be messed up. But what about data blocks? Okay, if you create a file, a Microsoft Word file, and this file is, I don't know, 30 kilobytes long, and one of the block is bad. Okay, how bad is that? Have you seen that? When you open a file, the file looks corrupted. Okay, so that can actually happen. Okay, but in that case, the directory structure is still intact. So, even though the disk block is bad, it's really not that bad. Okay, so hopefully you'll go to your backup and retrieve that file. If your directory structure is messed up, then that's more serious. All right, so what I'm trying to say over here is that, when things get out of sync on the disk, okay, there are different degrees of badness, and we try to make sure that, the file system is not messed up, even though some of the disk block might be messed up. All right, some of this one might be messed up. I mean, for example, you're in an editor, you try to, write to a file, and right when you click save, you lose power, right? Do you expect that file to be perfectly okay? Right? I mean, just when you click on save, you lose power, right? You go, oh, bad luck, right? So you know that the file that you just saved, might be bad. Okay, so we tend to accept that kind of failure as okay, because that's just bad luck. Okay, but if the file, the directory structure is messed up, then that's a big problem. You don't want to lose an entire directory tree because you just save a file. All right, so it's more important to keep the file hierarchy, the directory hierarchy intact than to keep every disk block intact. All right, so keep that in mind. Okay, so system file system. So over here is a picture. On the horizontal axis is consistency, how consistent the file system is when crashes happen. Okay, and the vertical axis is how fast these file systems are. Okay, so you can see that the file system that we talked about, system file system, and the fast file system, on the consistency axis, they actually perform really poorly. Okay, and this kind of system we basically used like 15 years ago. So if you use computers at that time and you lose power, chances are when you reboot the computer, or even if you have Windows XP these days, when you reboot the computer, you're going to see that it says checking disk. Okay, because it's possible for the file system to get out of whack, and then the operating system has to reboot to try to repair the file system. All right, so hopefully we don't really have to repair the file system very often. Okay, so these are old technology. In the consistent axis, they perform really poorly, but performance-wise, they're actually pretty good. Okay, system file system has poor performance. Fast file system has pretty good performance. Okay, and then comes an approach called soft update. We're going to talk about what these things are. Okay, it has better consistency. And then finally comes something called journaling or shadow paging. Okay, and these things are have high consistency. These days on Linux, when you run, when you create a, when you create a Linux machine, some of the system will ask you what kind of file system you want. Okay, so if you use ext2, then you are right here. This is ext2 is about right here. Okay, ext3 and ext4 is right here. All right, and of course, you're going to use ext3 and ext4, but if you read the description, you will see that, ext3 and ext4, they are journaling file system. Okay, so you say, is that a log structure file system? Well, it turns out it's really not log structure file system. It's a file system with journaling. Okay, we're going to see, and this is journaling is mentioned right here. Okay, and these are the systems that we use today. Okay, and Windows also have something very similar. All right, and over here, there's some comments that, these kind of, different approaches provide different kinds of consistency. The one that's provided by soft update is called recoverable consistency, and it's just a name. And then the journaling, they provide something called transactional consistency. And transactional, the word transaction is a term that's used all over the place in computer science. Database system use it. Networking system use it, operating system use it. So this word is actually more, more well understood term. All right? Okay, and we're going to see what these things are. All right, so over here it points out that, when you try to save a file, okay, and you get a crash right away, we're going to see messages on the screen. Maybe it says, file successfully updated. Okay, if you use a large buffer cache, when does the data actually get onto the disk? Okay, does it get onto the disk, milliseconds later, seconds later, tens of seconds later? So usually it gets to the disk, maybe a second later. Okay, maybe 5 seconds later. Okay, so you will see the message says successfully went to the disk, and then you have a crash. So you expect the data on the disk to be good, but turns out that might not be the case. All right. Okay. So, and also when data needs to go across the internet, you might say, stock successfully purchased. You got to make sure that when you see a message like that, there actually transaction happen all the way on the other end. Make sure that you actually has purchased the stock. You only see this message when the operation is completely finished. Okay. So for things that involve money, you're more willing to wait for it, okay, until it's completely done. But for things that you write to a file, you don't really want to wait until you get an acknowledgement from the file system, or you get an acknowledgement from the disk system to say that that data has went to the disk, okay? Because then you have to wait for a long time, right? So remember when we talked about the first part of the file system is saying that in order for you to write in a fast way, it's very difficult to do. And in the end, the only way that we came up with is the log structure file system. Okay, so what if you don't use the log structure file system? Well, then, if you wait for the writes to go onto the disk, then your application performance will be really, really poor. Okay, and we don't really want that. All right, so the file system consistency, right, is that, you have a state in your file system that's starting out looking something like this. Okay, so remember, what is a file system, right? The file system is to have data structures on disk. All right, so this is, one state of your file system. And what we need to do is that we need to modify, 2 places on the disk so that it looks like this in the end. All right, so we need to create a new block and update the old block to point to the new block. Okay, so that's 2 operations on the disk. All right, so the question is, how when you have 2 operations, you need to lock them together. Well, that's called, atomic, right? So you need to perform an atomic operation to have 2 disk write, okay, happens, as if it's atomic. All right, so disk is a very, very slow device. If you want to have 2 operations to be atomic, well, one thing that you can do, you can write to the disk and wait for it to complete, get an acknowledgement from the disk, and then write to the second one and wait for it to complete. And then you know that these 2 things, and during this time, nothing else can happen. Right, so you can use locking on the disk, but it's going to be very, very inefficient. Okay, and also, if you write one operation onto the disk, can you tell the disk not to crash? No, right? The disk, if it crashes, it crashes. Okay, so therefore you can't really lock these things together. All right, so we have to use a different approach. Okay, locking doesn't work. All right, so you have to write, these 2 operations on the disk separately. Okay, you can decide to, write this one first. Okay, and then you can write this one so that this guy will point to this. So that's 2 writes operation. The first one, you write this thing first, and then you write this one. Okay, so this one, you basically dirty the block, right, so that this guy will point to the right block, and then you write the disk. So now you end up with this situation. All right, so, so this seems to be a reasonable operation, because what happens is that if you crash right after you write the first block onto the disk, okay, what happens? Well, it's as if you didn't write that block onto the disk, right? Because when you reboot your machine, all you see is, is something like this. Okay, but if you're but what happens is that if you write this one onto the, if you write this block onto the disk first, so it points to this location, and then you write this block, but turns out that you have a disk crash or you have a system crash before this block writes to the disk, then this guy will point to the wrong place. Okay, so that's more of a problem. Okay, so it turns out that the timing, does matter. All right, so I guess that's what this picture is. Okay. In reality, what happened is that, because of the use of the buffer cache, you modify this block to say what is the file system has to look like in the end, and then you hand over those disk write operation to the lower level of the operating system. Okay, so do you remember who is doing that operation, writing the stuff to disk? Right, it's the pageout daemon. Right, remember the pageout daemon, when it try to look for to try to create space, it look at the pages that are not modified. If they're not modified, they move it from the active list to the inactive list, and they check whether the page is dirty or not. If the page is dirty, they will write to disk. Okay, so that's one kernel process that's writing things out to the disk. Okay, and also there is going to be another separate kernel process that basically just try to write all the the pages out to disk. If the pages are dirty, and then it will schedule these pages to go onto the disk. Okay, so those two things are sort of running in parallel. One is that one is for paging out, is that so that you can create free pages inside the kernel, and the second one is that you don't want to crash and have the file system to be inconsistent. All right, so both operation needs to write this page onto the disk. Okay, so the problem is that that's done using a different kernel thread, and that kernel thread doesn't really know that you should write this one onto the block onto the disk first, and then write this block onto the disk. So that's lower level of the system. It doesn't really know the order, so they might actually write data to the disk in the wrong order. Okay, if you write in the wrong order, then when you reboot, when you have a crash and you reboot, you might end up with an inconsistent file system. Okay, so over here it shows that you have a crash, but it's possible that none of these things can go onto the disk, or maybe one of them has got on the disk and the other one doesn't, and we don't really know which one. Okay, so this way, when you reboot, you might end up with this situation. Okay, in this situation, you might end up with an inconsistent file system. All right. Okay, so I guess that's a higher level, example. Let's look at a more realistic example. Right, this one is actually looking at the inode. Okay, this inode has a file that looks like this. It's using up all the 10 pointers, and now you're trying to, append one more block of data onto this, onto this file. Okay, so therefore the end result is that you have to use the 11th pointer in the inode. Okay, and this one will allocate a new indirect page, and then you allocated this page to actually hold the data. Right, so you have data here, you have data here, you have data here. Okay. This one is just, so this one is really not data for your file, right? This particular block, this data actually belongs to the file system. Okay, just like the inode belongs to the file system. Okay, so all the data over here on this side, this is considered file system metadata. Okay, and all the disk pages that are over here, this is your data or the user data. Okay, because this is the actual file. All right, so the pages on the disk, right, you need to separate. Some of them belong to the user, so these are user data. Okay, and some of the stuff are used by the file system, so this is, the file system metadata. Okay, so it's very important to keep the metadata intact, because if the metadata are not intact, then you have a broken file system. Okay, if you lose one of these pages, the user data, then you lost content in a file, but the file system is still consistent. All right, so we're going to distinguish these two type of data blocks. These two type of blocks that need to go onto the disk. All right, so in this example, okay, when you modify, right, when you need to append to this, append to this file, the block that get modified is this block, right? The inode block is modified, okay, because before this one doesn't have a pointer, now it's a pointer, so it's different. So this block needs to go onto the disk, and we're going to call this block X. Okay, this is a newly allocated block. Okay, so this is called Y, right? And it's part of the metadata. Okay, so so this is the indirect block, and then finally this one belongs to the user. It's block Z. Okay, so at the higher level of the file system, we say, oh, there are these 3 pages. We send it back to the lower level of the file system. Says write X, Y, and Z, X, Y, Z to disk, but we don't tell the lower level system which order do you write them. All right, so it is possible the lower level file system organize the writes to write X first, followed by Y, followed by Z. Okay, so in this case, if you write X to the disk first, and then write Y to the disk next, and then you have a crash, what will happen? Right, so let's go to, let me get rid of this stuff. Okay, so in that case, this will make to the, back out, right? This will make it to the disk, right? Because we write X already. This will make it to the disk, we write Y. And now Z, we didn't write to the disk. Okay, so this one will point to something wrong. All right, so how bad is this? Okay, so if you look at from the user's perspective, right, the data that the user wants to write, it doesn't really get on the disk. Okay, but in this case, what happened is that this particular block, well, it may be belong to a free list, okay? Because this block, was supposed to be, sort of a free block, right? You request a free block, and then you start writing data on it. Okay, what if you haven't really modified the operating system data? So this block is still on the free list. Okay, so now you have a pointer point to the free list, somewhere free block, and later on you're going to allocate this block to another file. All right, so that would be a problem. Now you're going to end up with one file belonging to, sort of one disk block belonging to two files. So even though this one doesn't really look that bad, but there could be bad news, especially later on. You have two users on the system, and one user can actually see the data of another user. Okay, so you got to be very careful, with doing these operations. All right, what if you write, this example, the lower level system decided to write Z first, okay, and then as soon as it writes out Z, so this guy goes onto the disk, okay, but X and Y hasn't written out to the disk, and then you get a crash, right? In this case, when you reboot the file system, when you reboot, you're going to get exactly this picture, okay, even though there's a block of Z that's being allocated, okay, and it has some data in it. Okay, so how bad is this? Right, so the only problem with this, right, I mean, when you reboot, all the users are happy, because nothing bad has happened, but now your file system has lost a disk block, right? This disk block is allocated, but nobody's using it, okay, so you're wasting disk space. All right, so in this case, after you reboot it for a few times, you're going to starting to have a lot of these disk block might be, floating around all over the file system. So you have to run some sort of another, kernel file system job, maybe called a scavenger thread, goes to the disk and try to look for all these blocks, and then, and then return them back to the free list. Okay, so that operation, you need to sweep the disk and look at every block and to figure out which block belong to the current file system and which block are free, and then find all the blocks that are supposed to be free, but they are not free, and then those things need to be returned on the free list. All right, so then that's the only way you can find this block, because otherwise this block, nobody can find it. Okay, so remember, right, when you go to the file system, you start with a super block. Okay, you should be able to find the entire file system, which means that you should be able to find all the blocks that are used inside your file system. Right, everything that's not being used, they're all free blocks, and all the free blocks belong to the free list. Okay, so the union of the file system plus the free list should include every block on disk. Okay, but then you're going to miss this block. All right, so that's why you need this operation once in a while to, to sweep the disk to look for all these blocks. All right, so this is not so bad. Okay, so in this case, we're lucky. Okay, we just need to, have a scavenger, task on the disk, on the file system to look for these blocks. Okay, but the first case is a little worse. All right, so how do you cope with this, different kind of, situation, right? So allowing the lower level of the file system to do writes in any order, that's really not a good way to go, because you're going to end up with unpredictable, situation. Okay, so you might end up with inconsistencies in the file system. All right. All right. So not allowing the disk to crash is not an option. Okay, so this is out. There are two approaches, as I mentioned before, and we're going to look at them. Right? One is called the consistency preserving approach, and the other one is transactions. Okay, so if we write the blocks out in the correct order, then we're not going to have any problem. Right? So the example that we see, the obvious thing to do is to write out the new node first, and then you write out the node that points to it. Okay, so in a way, if you look at the dependencies, right, this node depends on this node. Okay, this node doesn't depend on anything, right? So you write out the stuff that doesn't depend on any, the independent blocks go on the disk first, and then things depends on it go on the disk next, and then other things depends on the stuff that you just wrote, they go on third. Okay, so if you can figure out what depends on what, you can actually come up with a schedule to write the blocks onto the disk in a sequential manner. All right, so this actually can be done. Okay, so if you have a crash in the middle, right, this guy go onto the disk and the second one didn't, well, at least, you're not going to get a the file system inconsistency situation. All right, you might lose some data, but that's not as bad. and then you need a scavenger, operation to reclaim this block and put it back onto the free list. Okay, so this, this approach is known as soft updates. Okay, that you come up with the sequence and you tell the lower level of your file system to say, when you write these blocks out to the disk, do it in this order. All right, so that's a that's a very straightforward operation. Okay, so if you have a situation like this, okay, what order would you ask the file system to write? Well, again, you analyze the dependencies, right? The block Z doesn't depend on anything, so you schedule Z to go out first. Okay, block Y only depends on the stuff that doesn't have any dependencies, so you schedule that to write out next. And then block X, after you write out Y and Z, then you can write out X. So therefore, you can actually figure out the dependency, says that I have to write this in that order. And if you're implementing soft update, you will pass that description of what the order these things has to be written to the lower level. And the lower level have to follow the schedule. Okay, so in that case, if we look at the crashes, what if the system crashed here? Right, the system crashed here, then you have the old file system image, right? You only have these 3 blocks, and this one is old. Okay, so that's okay. If you crash right here, it's still okay, right? Because these 2 things got onto the disk. If you crash, if you crash right here, again, these 2 things onto the disk is still okay. Okay, and if you crash right here after X is written, then you have the new image. All right, so basically, anytime when you crash, if you crash earlier, you're going to have the old system image, and if you crash after X is written, you have the new system image. All right, so the idea over here is that no matter when you crash, your file system will be consistent. All right, what about the case when you try to write to disk, and then when you try to write to disk, and X get corrupted? Okay, the disk just happened to lose power when X was writing to the sector. All right, can that happen? I mean, not with modern disk. Now, modern disk, basically, when you try to write to disk, okay, even if you lose power, the disk is going to have some kind of a battery backup so that it will finish the last operation. Okay, so the operation on disk either doesn't happen or it happens. So when you try to write a sector onto the disk, it's kind of like an atomic operation. All the bytes in the sector go onto the sector, or none of them make it to the sector. Okay, so when you try to write the X block onto the disk, either it makes it or it doesn't make it. If it doesn't make it, it's as if the crash happened right before X. If it makes it, then it's like the crash happened right after X. All right, so if you use the soft update approach, no matter what we do, the file system is going to be in one consistent state or in another consistent state. It's always going to be consistent. All right, even though you might have blocks that are floating around that you need to gather, later on. All right, I guess the picture shows you that, if you crash before, you have the old image. If you crash right here, okay, you still have the old image. If you crash right here, it has the old image. And then if you crash here, you have the new image. Okay, so the file system is always consistent. Here's another example, creating a new file with one data block. Okay, so in that case, how do you create a new file, right? You need to allocate a new inode. You need to have it belong to the the parent directory. So therefore, the before image when you do this operation is that you're going to have some kind of a directory that contains this new file, and this directory need to be updated, right? So this directory need to be updated, and you create a new file, have a new inode, and some new data. Okay, so this picture looks exactly the same as before. You have X, Y, Z. 3 of them, right? If you write out the block in this order, then it's not going to work. If you write out in this order, Z, Y, X, then you're doing soft updates, and then no matter when you crash, the file system will always be consistent. All right, this is actually no good. Another example, moving a file, right? So you have, this is your original image, right? You have this file belong to this directory, and now you want to move this file into this other directory. Okay, so remember, move is what? You have implemented that in, kernel 2, right? Move is doing a hard link followed by a remove a link. Okay, so you create a hard link from here, and then you remove this link. Okay, and that's how you do the move operation. Okay, so in this case, how should you write to the disk? Okay, so if this file is already created, right, then you only have 2 things you have to write. You have to write the new Y and the new x. Okay, you can write it in any order. All right. So over here, this is x and y. This is y and x. Okay. If you write x to the disk first, okay, then what happens is that y hasn't been written on the disk yet. Okay, so this is bad, right? Okay, this means that you're going to lose the file. Okay, and so that's really not good. This one, what about if you write y first and you write x, right? If you write y first, okay, if you write y first, and then if you haven't modified x yet, then if this is x prime, then the x prime is going to point to this one. Okay, which means that your true operation basically is a link followed by an unlink. The link is finished, but the unlink is not finished. Okay, so this way it's as if you have just created, instead of doing a move, you did a link. Okay, so this file is going to have a link count of 2. How bad is this? Okay, so this one you didn't lose the file, right? The file system is still in a consistent state. Okay, but this might not be good for a security reason, because if you are on a file system, for example, if you have 2 files that somehow you have, let's say that on Nunkey you have a file and you want your friend who has another account to link to this particular file, so they link it, right? And then if you try to unlink it and you want to make this file belong to the other user, but now you have a system crash, you end up 2 people sharing the same file. Okay, but in your mind, you thought that you have already moved this file to another user, but turns out, both people still have access. So your friend thinks that you don't have access anymore, but turns out you still have access. Okay, so this could be, kind of a security issue. And of course, we can do this in the kernel, where you try to move one file from one user space into the space of another user, and you end up having, that file being shared. Okay, so this one, it's really not that great. Okay, so this case, you might even create some kind of a consistency issue if you are, not supposed to share these 2 files. Okay, so in that case, which way is the right way to write? Well, you're going to have a problem either way. Okay, so this is why soft update doesn't really have, perfect, consistency. Okay, so we sort of put it in the axis of consistency somewhere in the middle. It's better than the fast file system, but it's worse than the transaction. All right, because of a problem like this. All right. So how do you implement this? So the idea is very simple. You analyze the dependencies of these blocks, okay, and then you write them in the right order, okay, and then you're done, right? So the problem with x and y there is that if you go back to the previous picture, okay, if you analyze the dependencies of x and y, which one depends on the other one? Well, none of them depends on the other one, right? So therefore, that's why this operation fails, okay? Because when you analyze the dependency of x prime and y prime, you realize that they don't depend on each other. So you say, oh, any order is okay, but turns out it's really not that okay. All right? Okay, so over here, I guess over here it says, well, the idea is very simple, but in reality, it's a little more complicated. Okay, and this one is assuming that the file system performance is important. Of course, the file system performance is always important. So one of the problems with the soft update is the following. Okay, so over here we have this situation where you have a directory inode point to a file, and this guy also point to a file inode. All right, in this case, you have 3 disk blocks. Okay, you write to the disk. Obviously, if you perform analysis, and if you have taken CS570, or you probably heard of some one algorithm called the topological sort. In topological sort, you basically can represent this as a graph, and then you perform topological sort to figure out what dependencies are, and the dependency will tell you which block to write to the disk first. Okay, so in that case, it will say this is number 1, this is number 2, this is number 3 as the output of a topological sort. Okay, what makes that doesn't really work in reality is that the operating system tries to save space on the disk. So what it will do is that it might decide to pack a few data objects together. Okay, what if the operating system or the file system decide to pack these 2 guys together into one disk block? Okay, the disk block might be very large. Okay, 8 kilobytes or something like that. and you don't really want to have too much internal fragmentation. So you may end up saying, oh, these two objects, I want to put them in the same disk block. Okay? So if these two guys become the same disk block, and now what does the dependency graph look like? If this becomes one block, you have one arrow coming out from here to here, and one arrow coming from here to here, and that's circular dependency. Okay? If you know about topological sort, you know that topological sort break down when there's circular dependency. If there's circular dependency, which one do you write first? You know, then you can do it. Okay? So this will mess up topological sort. So one way to do it, people actually, who's implementing soft update, they say, well, we can actually make it work by breaking circular dependencies temporarily, and then, restore the circular dependency. Okay? So the idea over here is that, you start with this thing that have a circular dependency, and then because you have more information, you know how to break this thing up in the middle. Okay? So what I will do is that I start with this node, I'm going to modify this page in memory by modifying the bottom part of this page in memory. Okay, I'm going to write out this entire data onto the disk. So this is number one. Okay, and then I'm going to write this out to disk number two. And then I'm going to modify the top part of this data, modify this page, and write the entire page out to the disk again as number three. So 1 and 3 are the same memory block, but in between we write on the new data onto that particular block. Okay, so this will go back to the previous picture as 1, 2, 3. Okay, because you need this, you use this special knowledge to say that, oh, it's the same block, and if we have the old data on there, then we can go back to this picture. Okay, and then we can figure out how to write this in three steps. All right. But if you read the textbook, what it says, well, this needs to be done in order for this operation to be fast. You actually have to do it at a very, very low level, and you have to wait for the operation to finish. Okay, so therefore, you have to write this one first out, write it synchronously, meaning that you have to wait for this operation to finish, and then when it finishes, you immediately write this one finish, and then eventually you can write the last one. Okay, so it's a little tricky to do this just right at the very, very low level of your operating system. Okay, so this is the way to sort of break circular, circular dependencies and still have soft update to work for you. All right, but still leave soft update with the previous problem. Okay, so there are actually systems that still use soft update these days, and in these systems, the disk updates may be several seconds behind, writing to the buffer cache. All right. All right, the other approach, the better approach, is called transactions, okay? The basic idea is to group disk writes into something called transactions, okay? And again, transaction, I think the idea of transaction originally came from database systems, but it's such a good idea that everything started using it. Distributed systems using it, operating system is using it, networking is using it. All right, so what is a transaction? So basically, if you want to write a few things to the disk, you sort of say you group them into one transaction. Okay, so these are the things that you want to do to the disk. Okay, X, Y, Z or something like that, right? Okay, what you do is that you put them inside a transaction. Okay, and this transaction satisfy the ACID property, ACID. A stands for atomic. Okay, which means that either all X, Y, Z are done or none of them is done. Right, which is what we want in the previous case, right? When we try to write to the disk, either we want X, Y, Z all to be done or nothing to be done. All right, so this is a good thing, right? The second one is that it's consistent. The C stands for consistent. It takes the file system from one consistent state to another. Okay, so if you look at this time over here, right? This is time. Okay, over here, the file system is in state 1, and then over here it's state 2. All right. If the transaction is performed, the system will be in state 2. If the transaction is not performed, it will be in state 1. Okay, and over here you have the transaction going on over here. It's either done or not done. Okay, and it will. So if you do transaction, then if anytime when you look at a system, it's always going to be in a consistent state, because transaction can only take the system from one consistent state to another consistent state. All right, so there's no way for your system to be an inconsistent state. Well, I mean, it's not no way. I mean, if you have a programming error, then of course, if you put the wrong thing in the transaction, yeah, then bad things can happen, right? So if you don't have programming bugs, okay, then your file system will always be consistent, right? That's why it's high on the consistency axis, okay? And the other thing is that I stands for isolated, okay? It had no effect on other transactions until you commit it. Okay, which means that if you look at this time axis, right, if this transaction happens, it takes the system from S1 to S2, okay? Anytime when you try to look at the system, you say, what system are you, what state are you in, okay? If you try to look at this system at this time, it's in state 1. Okay, over here, I guess there's S0, right? If you look at it this time, it was the S1. So now you start your transaction somewhere between this time and this time. Okay, so if you ask your system, what state are you in, even at this time, right here, it will say my system is state S1. Okay, whatever that you do over here, okay, are isolated from these other operations or the system state. Okay, but as soon as you pass this, this point is called transaction commitment. Okay, if the transaction is committed, right after, so it's until committed. As soon as transaction is committed, you come and ask, what state are you in? The system says, I'm in state 2. All right, so there's no interference between, this transaction and the rest of the system state. Okay, and also there's no interference between this transaction and other transaction. So if you look at the system evolution over time, it goes from one state to another, to another, to another. It's very clear cut. At any point in time, you ask the system what state you're in, it knows exactly what state it's in. All right? And finally, it's durable. These operations, when you take it to beyond, state 1, after you commit a transaction, even if you do a crash, even if your system has crashed, when it reboots, it will be rebooted in the system 2 state. Okay? If you have a crash right before the commitment time, you're starting to do these operations, and the system crashed right here, when you reboot the system, it will go into the S1 state. All right. If it's committed, then it persists. It will stay in the file system. All right. So that's nice property. The question is, how do you implement this thing? Here's an example of a transaction. So actually, we do transactions all the time. Right. The classic example from database is transfer $100 from account 1 to account number 2. Okay. How do you transfer money from one account to another? So it turns out that, for bank accounts, there's really no transfer operation, right? It's just like writing to disk, okay? There's no way, to do two things at the same time. What you would do is that you would decrement $100 from account number 1, and then increment, the second account from, by $100. Okay, that's how you transfer $100, is to have these two operations, and you want to lock them in a transaction. Right? And the reason is that because if you don't lock them in a transaction, you get a system crash right here, you're going to lose $100 in your bank account, right? And then you're not going to be very happy. Okay? So you want to do this operation, these two operations, while satisfying the asset property, and therefore you put them in a transaction. Okay? So the idea over here is that we put them in a transaction, we lock these two things into one atomic operation. All right? So either they are either both done, or none of the operations are done. Okay? It doesn't matter which operation you do. I mean, if you have a transaction that guarantees that this is all done or none of them is done, doesn't matter which one you do first. Right? I mean, if you have the guarantee that they're all done or none of them is done, then it doesn't really matter, I do this first, I do this next. Because if I end up by doing this one first, okay, and I have a crash, okay, then the semantics of transaction guarantee that, well, it's either all done or it's not done. Right? So therefore, what I need to do is either revert back to the previous state or move forward to the new state. Okay? Because I'm running transaction semantics, then, whatever operation that was done either needs to be, either you have to undo that operation, okay, or you have to do another operation so that everything in the transaction, they all get completed or they all get taken out. All right, so in order for you to implement it, you got to implement the operation either to roll back a transaction, something that you have done, you have to undo it, okay, or something that you haven't done, you have to do it. All right, so that's the way to implement a transaction. Okay, so this means that, So how do I, how do I do something like that? Okay. Okay, if I have to do these two things, right? So, for example, if you're a forgetful person, okay, and then, you're asked to go to the grocery store and buy, two things, how do you make sure you buy them? You're very forgetful, right? Once you buy one thing, you tend to forget what you need to buy. Okay, so what you do is that you bring a journal with you, and on the journal you write, I have to buy number 1 and buy number 2. All right, so what you do, you go into the store, you say, oh, I have to buy number 1. You go to the aisle where number 1 is, you buy the number 1, and then you forgot what you need to do. Okay, you basically have a system crash, right? You have a system crash, and you forget, so what am I supposed to buy? Okay, then you go look at your journal, say, oh, I have to buy number 1. Number 2, you check your bag, you say, I have number 1 already. So therefore, I have to buy number 2. All right, so basically, you use a journal. So this is like a journaling file system, but it's really not a journaling file system because the journaling file system is a file system. This one is really not a file system. It's just a little convenient thing that you use to keep track of your write operation. All right, so we're going to bring a little journal. On the journal, we're going to say everything that we need to do. All right, so that's the journal that's mentioned over here. So the solution is to use journaling. Okay, we're going to write a little journal to say what needs to be done. Okay, and then, when you recover from a crash, you look at the journal and says, oh, what are the things that has been done and what are the things that hasn't been done? And there are 2 ways that you can do it. One is to go back. So let's say that you have a list of 4 things, or in our example, you have X, Y, Z in the list. Okay, and then you know that you have checked off why Y is done. X and Z is not done, right, for whatever reason. Okay, so now what you can do is that you can either revert Y to the previous state, okay, or you want to perform X and Z. Okay, so depending on what your choices are, that that makes these implementation into 2 different categories. One is called undo journaling, and the other one is called redo journaling. Okay, the undo journaling meaning that this journal that you wrote, you got to write down how to go back to the previous state. Okay, so this is undo journaling. It tells you how to undo an operation. Right? We all know how to undo, right? When you use a word processor, you can say Control Z, you can back to the previous state. Okay, so that's because in Microsoft Word, they remember what the previous state was, so that when you do Control Z, you can go back to the previous state. All right, so that's undo journaling. Okay, so in that case, in the journal, you will have to write the before image of X, Y, and Z. You will say that, X, Y, and Z, this is what they look like before I modify X, Y, and Z. Okay, so therefore, when you recover, you want to undo X, Y, and Z. You can write X. Okay, so X will be the old X. This is the old X, and this is the old Y, and this is the old Z. All right. So when you recover from your crash, what you will do is you will write X back to disk, Y back to disk, and Z back to disk. All right, so it doesn't really matter whether you have modified X or modified Y or modified Z already. Okay, as long as you write the old image of X, Y, and Z back to disk, do you go back to the previous state? Yes, right? Because you go back to the old state because you just restored all the content of the old X, Y, Z. Okay, if you modify Z or Y already, well, then you go back to the old X, Y, Z. If you modify Y and Z already, again, you go back to the old X, Y, Z. So you take your system back to the previous state. Okay, so if you're implementing undo journaling, when you recover from the crash, as part of your crash recovery effort, is that you go to your journal and then undo everything in your journal. Okay, and then you know that you're going to return back to the previous state. Okay, the other one is the redo journaling. So this one, instead of containing the old X, Y, and Z, this one is going to contain new X, new Y, and new Z, and then put them in the journal. Okay, so in the journal, you write, these are what the new X, Y, Z is going to look like. Okay, and now when you crash from the system, you don't know if X, Y, Z, which one has been modified. You don't care. What you will do is that you will write the new X to the disk, and you write the new Y to the disk, and you write the new Z to the disk. And now is the system in the new state? Yes, right? Because X, Y, Z will take the system into the next consistent state. So in this case, this is the redo journaling. So inside the journal, you have to write the after image. Okay, so after image means the new image. Okay, so this way, when you recover from the crash, then you're guaranteed, if you just look at the journal and redo all these operations in the journal, even though they are done already, you can do it another time. Okay, so basically I have the after image. I want to redo all those after image. Now I'm going to take the system to the new state. Okay, what if in the middle of doing this updates, writing the new X and Y to Z, I have another crash? Do I have to worry about that? No, right? Because when this happens again, I'm going to go back and the journal is still there, right? The journal is something I've written already. I'm going to go to the journal. I'm going to write X, Y, and Z over to the disk again. If I crash again, I'm going to do this over and over and again until X, Y, and Z are onto the disk, and now I'm in the new state. All right, so this is the the redo journaling. Okay, so one little problem, right? In the previous example we saw, we say decrement account number 1 by $100. Okay, if we do that 100 times, okay, you're going to be out of money, right? Okay, so that's why it's important to see that over here it says you write the after image. You don't describe the operation. If you describe the operation, then it's going to be problematic, right? Decrease $100, decrease $100, decrease $100. Okay, what you do is that you write the after image. So if account X right now has $1,000, you want to decrement by $100. You say account, the account number 1 now has $900. Okay, if you write account 1 has $900, you can write it 100 times. That's going to be the same thing as writing one time. Okay, so therefore, what you put inside this, inside this journal has to be certain, the only thing you can put in there is before and after image. Okay, you cannot put operations, into this journal, okay, because that doesn't work. All right, so in a way you can say that, these things are, if these things if you think of them as operation, then the only kind of operation that you can do are the one that you can do it over and over again. And there's a word for it. This is called idempotent. Okay, so the only thing that can go inside of a journal are idempotent operation. Okay, idempotent meaning that if you do this 500 times, it's the same thing as doing it once. Okay, certainly increment and decrement is not idempotent. Okay, all right. So journaling is one approach. Okay, and the other way to do transactions is called shadow paging, and we're going to see what that is all about a little later. All right. So. Okay, so a journal, so what is a journal, right? So journal is, this is a little notepad you take to the supermarket, right? So it's, it's different from the state inside your house. Okay, so it's not part of the operating system. So it's not part of the file system where we describe, all the files and all the free lists and stuff like that. So the journal, it's a separate part of the disk. Okay, if you take your disk, right, you're going to say that, this part is the journal and this part is the rest of the file system. Okay, and you can add journaling to any file system. Okay, if you have FAT16, FAT32, whatever, ext2, whatever, any system, you can actually add journaling to it. Okay, so this becomes a very useful tool. Any file system that has poor consistency behavior, you want to make it have a good consistency, well, add journaling to it. Okay, what you need to do is that you need to use a separate part of the disk. You need to take out part of the disk and say that this part of the disk is going to be used as journal. Okay, so that's why this is very different from the journaling file system, right? The journaling file system is that this is the journaling file system. Okay, the file system itself is a journaling file system. Okay, and adding journaling to a file system for the reason of crash recovery, okay, it's very different from having a journaling file system. All right, so this part of the journal is kind of like the journaling file system. It appends only. Okay? Well, actually, over here it says append only. It doesn't really say, you never modify it. Okay, so it turns out that, the way you use the journal is that it's append only, right? So over here, I guess we can draw this horizontally. You append stuff to the journal. Okay, and then the other operation you can have on the journal is to wipe it out. Okay, remember, right, in the journaling file system, it's append only and never delete. Okay, in a journal for these file system, okay, it's append only, and then the other operation is to wipe the entire journal out. Wipe it clean, start with a new journal. All right? Okay, so it's like a log. For redo journal, we're going to focus on redo journal. Okay, undo journal, they sort of do that on database systems. In the operating system, they tend to use the redo journal. Okay, so we're going to focus on the redo journal. In that case, you only append what you are going to write to the main part of the disk. Okay, so therefore, what you write on the disk is the new image of X, Y, and Z. All right, so inside this journal, you write the new image of X, the new Y, and the new Z into the journal. Okay, and also at the end, you write something called a commit record. Okay, so you write this little like a thumb tag. You write a little tag in there to say that this is the end of a transaction. Okay, so if you look before X, Y, and Z, there's going to be another commit record, and then there's some A, B, C, and then there's another commit record or something like that. Okay, so inside the journal there will be one transaction followed by the end. So this is like end transaction. Okay, so there's one transaction, end transaction, another a few writes followed by end transaction, another few writes followed by end transaction. Okay, and over here again, XYZ can be written onto the disk in any order. The order doesn't matter. Okay, so the lower level of the operating system or the lower level of the file system can decide what is the fastest way to write all these blocks out. All right? Okay, so this commit record, the commit record, so XYZ can be a file and can be a really large file. Okay, the commit record is always one disk block in size. As I mentioned before, when you try to write one block onto the disk, either it gets on the disk or it doesn't get on the disk. Okay, because it's only a single block or a single sector. So this block, when it goes on the disk, okay, it's either get in there or not. There's nothing in between. Okay, the disk, the disk actually can guarantee that it's either written or not, using hardware on the disk, and again, the disk has batteries and stuff like that to make sure that the operation is either complete or didn't even get started. All right, so you can actually always look at the journal and look for commit records. Okay, you're not gonna get confused. All right, so the idea over here is that before we modify the main part of the disk, before we modify the file system over here, we're gonna write to the journal here. Okay, write a bunch of transaction onto it, right? Transaction, and write a commit record over there. Okay, whenever we finish writing to the journal, that's when we start updating the disk. Okay, so basically you would do this thing with two different, threads, right? One, update the journal. When it's done updating the journal, you can tell the rest of the file system, say, okay, go ahead, write it anytime you want. Okay, and the other thread will start picking up from the beginning of the journal and start writing all the transactions to the disk. All right, so they will look for, a transaction record boundary, modify whatever that's out here, okay, wait for it to all get done, and then look for another, end transaction, the commit record, and write, ABC to the disk, okay, and then look for this thing and write XYZ to the disk. Actually, they don't have to wait for the operation to be done. Actually, they would just start going this like crazy and try to write all this block to the disk, okay, and it will only write stuff where it sees the commit record. If the commit record is not there, then it's not going to write out the last few blocks in the last transaction. All right, so what happens is that when you do all these writes to the disk, right, so in the journal, you're going to have one transaction followed by another transaction, and the last one, if you don't have the commit record, then the last one is not a transaction. If you have the commit record, then the other one is the last one is a transaction. All right. So what happens is that if you get a crash on the disk, what do? Okay, you're gonna you reboot your operating system and you see that you have a journal right here, and inside this journal you have transaction 1, transaction 2, and transaction 3, and we are doing the redo journal. Okay, so all you have to do is to write out all these records again. Okay, because this is a redo journal, right? So does it matter, so over here, let's say that over here you have 4 blocks to write, over here you have 2 blocks to write, over here you have 3 blocks to write. Does it matter which blocks out of these 9 blocks have already gotten to the disk? I mean, it doesn't matter, right? Because what you're going to do is, again, you're going to rewrite all these 9 blocks with the after image and write them to the disk. Okay, so you're not going to let the operating system to continue to go on until you finish writing all these 9 blocks to the disk. Because you know that when you finish writing all these 9 blocks to the disk, you will be in a consistent state. All right? So over here, if we look at this as if this is time, right? Before this, your system is state 0. After you finish transaction 1, you will be in state 1. After you finish transaction 2, you'll be in state 2. After you finish transaction 3, you'll be in state 3. So in this case, if you redo all these 9 operations, writing all those 9 blocks onto the disk, you're guaranteed that your system state is going to be in state 3. All right, so in this case, the 2 states that your system could be in is going to be either in state 0 or state 3. Okay, but whenever we reboot, we know for sure that it will be in state 3. Okay, we're going to refuse to let the system to move forward until the system is in state 3, and then we continue to boot the operating system, finish booting the operating system. Okay, so the redo journal is very, sort of simple to implement. Okay, and when your recovery is also simply done, right? You have to hold the operating system. So whenever you get a disk crash, when you reboot your system, it's going to take a little longer because you have to write out all the stuff in the journal, okay, to the disk, right? And then you can continue. So what do you do when you continue? You wipe out the journal, right? Because if I finish writing all these things to the disk, okay, then I know the system is now in S3, right? So therefore, I can erase the journal and then start from the beginning again. All right, so actually I can do this also very often. Every time when I start writing out all the operation, all the data to the journal, I need to communicate with the lower level of the file system says, have these 9 blocks has been written out to disk? If it has, I can actually delete the entire journal. Okay, so whenever I try to append a new, so once in a while when I append new stuff to the disk, maybe I say, well, maybe I want to do a checkpoint operation. So this is kind of similar to in the journal file system, right? You have a checkpoint file. Okay, over here we can do a similar thing. It's called a checkpoint operation. Is that you look at all the disk blocks that are in your journal and make sure they're all written to disk. Okay, when you perform the checkpoint operation, if they are all onto the disk, then you can delete the journal. All right, and when you're performing the checkpoint operation, if not all the blocks are written to disk, what you do is you wait until they all go onto the disk, and when you wait, you're not allowed to append anything more to the journal, right? Because you want to work on that I said. Make sure they entirely go to the disk. Then you delete the journal. You start from the beginning again. All right, so that's what needs to be done in the system, and this is relatively simple to implement. All right, so over here, I guess the note down here says, after recovery, the state of the file system is what it was at the end of the last committed transaction, right? Over here is state 3 right here, okay? After state 3, if you start writing stuff to it, but before you write a commit record, then it's as if they are not present. So therefore, you only, redo everything up to the end of the previous committed record. All right? Okay, so what could be the problem? What if X is a 1 GB file? Right? I mean, we said we're going to reserve a part of the disk, for the journal, and the journal is after image. So if you just create a 1 GB file, is the journal has to be 1 GB long? So that's a problem, right? The journal can't really hold all the data. All right, so that gives you 2 options. One is called journal everything. Okay, so in that case, if you want to create a file of 1 GB in size, well, you have to have a journal that's that big, so you can write all the after image, right? Because the rule is that you're only allowed to modify the file system after you have written your journal. Okay, so therefore this could be a problem. Okay, so journal everything is very wasteful in space potentially. Okay, but what is the advantage of journaling everything? Is that when you recover, you're not going to end up with file data disappearing. Okay? The other approach is to journal only the metadata. Remember, right, last time I showed you how to divide things up between metadata and data, right? Metadata are the one that belongs to the file system to keep track of inodes and, all those things that with pointers, they're all part of the metadata. Okay? And the user data are the actual data. So in this case, any disk block that belong to the user data, you don't add them into the journal. Okay, so it is possible when you do recovery, you're going to recover everything that belongs to the file system. So all those pointer blocks, they will all be consistent. But whatever they're pointing to, there's no guarantee that those data will have the user data in them. All right, so in that case, as long as you write to the disk often enough, when you have a recovery, the user might lose data in the last, 5 seconds. All right, is that acceptable? I mean, these days we say, well, it's kind of acceptable, right? Because, when you reboot your machine, if you have a desktop, you can actually unplug the power cord at any time, okay, and then plug it back in, right? And then, if you don't write to the disk in the past, if you don't modify your file in the past 5 seconds, then chances are when you reboot it, everything will be there. Okay, so unless you're doing something in the last 5 seconds, yeah, then maybe those things are lost. Okay, so usually that's pretty good these days, and that's why if you have a Linux machine or you have Windows NT, what you can do is that, when you're ready to shut down, you can just press the power button. Okay, because chances are when you go to the power button, when you try to hit that button, it's been 5 seconds, so everything's already go to the disk, so you're not going to lose anything. Okay, if you do this Windows XP, it's going to be really bad news. All right, so all these things are implemented in the file system. These are file system features to have crash resiliencies. All right? Okay, so I guess if you try to do metadata, right, so this one, again, you label the data carefully and only write the metadata changes into the journal, and then the user data, they can be written to disk whenever, the file system want to write to it. Okay, so this one is relatively fast, and also the journal doesn't have to be a really, really big space that you reserve onto the disk, to just for journal. All right, so again, pointing out the main difference between the log structure file system and journaling, because both of them use a log, okay? The main difference is that log structure file system is a file system, okay? And the purpose of the log structure file system is to improve write performance. Okay, so whenever you try to write to the disk, it's always a long write to the disk, and they are all right next to each other. Okay, so that writing performance is good. Okay, to improve the read performance, how do you do it? Well, use a buffer cache. Okay, so this is sort of the last step to try to use 100% of the disk performance. In that case, if that's important to you, well, then you will use the log structure file system. Okay. Otherwise, journaling, the journaling that we just talked about, it's for crash resiliency, and this kind of journal can be added to any existing file system, right? The picture I drew over here, this is the journal, right? This can be any file system, okay? Windows, Unix, Mac, or whatever, it doesn't matter. All right, so again, back to this example, okay? If you have, if we modify X and Y and Z, okay, what we will do is that we write the after image of X, Y, and Z into the journal. We write the transaction record, okay, and then we let the file system to write X, Y, and Z from the buffer cache onto the disk at any time. Okay, so remember the journal is not part of, this, okay, it's on a separate part. Okay, so therefore you write this thing first, and then you let it go ahead for the rest of the file system to write X, Y, Z onto disk. All right, so then the only thing that matters is whether you crash before this thing get into the journal or after it, right? This is the commit record. If the commit record get onto the disk, if the commit record go into the journal, then you know that your system will be in the consistent state after XYZ has been written to disk. Okay, so that will be in the new state. If the commit record didn't get on the disk, you have a crash, then you know that you have the before image of the system before XYZ has been modified. All right. Okay. So I guess these two situations are mentioned over here, right? Again, in the bigger picture, okay, you will have a disk look like this, right? Super block and things like that, and then you reserve part of the disk as your journal, and the rest are the file system where the XYZ actually go in over here, and over here you store the after image into your journal. Before you let the rest go ahead. All right, so ext2 on Linux is a FFS clone. Okay, the file system was an improvement over system file system. And I think a while ago I mentioned the fast file system is actually very popular. Lots of the current Unix and Linux file system came from FFS. Okay, ext2 is pretty much exactly FFS. Okay, so it has the problem of crash. When you crash, you need to take a while to recover. Okay, ext3 is simply ext2 with journaling. Okay, that's all it is. Okay, ext2 has all the feature of the fast file system. Now you just add journaling to it. Now it's all of a sudden it's resistant to crashes. Okay, and I guess there are some of the detail which I mentioned already with checkpointing. All right, so the final approach that we want to talk about, this is again another way to do transaction. Okay, and this is very different from the previous way of doing transaction. The previous way of doing transaction is basically the way database systems do transaction. Okay, and again, if you take in a database class, they will tell you about redo journal, undo journal, things like that. This is called shadow paging. Okay, the idea over here is based on copy on write. Okay, and there are actually systems use them. One is the waffle file system by Network Appliances, and the other one is Sun's ZFS. All right, the shadow paging idea is very, very simple. Okay, but I guess the problem is that you can't really add it to any existing file system. Okay, that's why the people don't use it. Journaling is very, very simple. You can just add it on to any file system. So, I mean, at this point, I don't know if you have the appreciation that the file system, the entire implementation, even though we only implement the virtual file system, we haven't really implemented the actual file system. You can sort of imagine that the actual file system gets pretty messy, and it's hard to get it just right. Okay, so once you get the system just right, you don't really want to muck around with it. Okay, so you don't really want to add, features like, shadow page thing onto the existing file system if it's working. All you have to do is to add a separate thing called journal, and then, implement your file system that way, right? It's much easier to add journaling. All right, so if you look at all the pages in your file system, they sort of naturally form some sort of a tree, right? And here's the root of the file system, and you follow the inode, they will point to all these files. So the file system is sort of in a hierarchy. Sometimes things are being shared. Okay, so but you can sort of draw a picture like this. Okay, and these are all the busy all the blocks that are committed to being used in the file system. All right, I'm not drawing any of the free blocks. Okay, so you can find all the blocks that are used in the file system, and then they form a hierarchy this way. Okay, so now what I'm going to do is I'm going to perform copy on write on disk pages. All right, so what's going to happen over here is that if I need to modify this particular page, okay, following the copy on write principle is that I'm going to make a copy and then only write to the copy, right? I'm never going to write to the original data because I'm doing copy on write. Okay, so what I'm going to do, I'm going to make a copy of this page, allocate a new page right here. Allocate a new page right here, and then copy this thing over here. Okay, and then I'm going to change the data right here. Okay, so now I'm labeled this guy blue because the blue is different from the yellow. All right, so what's wrong with this picture now? Right, the picture now is this pointer is pointing to the wrong place. Right, because now I just modified this, this particular page. So since I'm doing copy on write, I need to adjust the pointer to point to the right place. So this guy I need to point right here. Right? How do I modify this pointer? Well, I got to use copy on write again. Okay, so this guy is changed. So therefore, I need to do copy on write. Okay, I'm going to make a copy on this guy. Okay, so when I make a copy on this guy, then this pointer right here will point to this guy will point to here. Wherever this old thing was copying to, I'm making an exact copy. Okay, and then I'm going to write to the copy. I'm going to change this pointer to point to this one. All right, so what's wrong with this picture? Well, this guy now points to the wrong place, right? Okay, so this guy needs to point to this guy. So therefore, again, copy on write. I made a copy of this one. Copy the entire thing over, adjust the pointer, so this guy will point to this guy right now. Everything else is exactly the same as this page. Okay, what's wrong is this pointer is pointing to the wrong place, so therefore I got to modify that again by making a copy. Okay, and then all the other pointer will point to the right place except the last one, so I modify the last pointer over here. Okay, now this has become a different one. Okay, and now this pointer is pointing to the wrong place. Okay, so then I need to perform another copy on write. And this time I'm copying the root, right? Everything is the same except the last pointer. I adjust the last pointer, and then this guy is the new root. Okay? when I write to the disk to say that this is the new root, right, in VFS, you know where the root is, right? You know the inode for the root, okay? So now I'm going to record that now I have a new inode for the root, okay? This is the new root. All right, so that, you know, the root inode is going to fit in one disk block. So when I update the new root, or update where the new root is, okay, that's like a commit record. Okay, so I'm going to record somewhere on the disk to say that this is the root, okay, writing down the inode number. That's a single sector write, okay, so either that thing get written on the disk or not. Okay, if it didn't, if it didn't go on the disk, if I reboot the file system, what would the file system look like? The file system will look like the yellow file system, right? If I reboot, right? If I reboot at this point, this hasn't gone to the disk, okay? Am I going to be able to see this block? No. Would I see this block? No. Would I see this block? I will not see any of the blue blocks. Those blocks will be allocated on the disk, so later on I just have to collect them, right? This is almost like the soft update, right? I might end up with these blocks that are floating around, so all I have to do is to do like garbage collection, or I call it a scavenger operation, to recover, you know, all these blue blocks. But when I reboot, I still have the old file system. It's as if nothing has happened, okay? But if this one got onto the disk to say that this is the new root, okay, then I have a new file system. Okay, so does the file system go from one consistent state to another consistent state? Right, I mean, the answer is yes over here, because the only two states are allowed to exist, either the yellow state or the one with the blue stuff all in there. All right, so this is another way to, to implement the file system so that I have a transactional consistency without actually having the transaction in there. Okay, because this one is the only commit record that you have to write. All right, so that's it. It's a very simple scheme. It's surprisingly simple. Okay, so why is no file system using this? Okay, because you can't add this to any existing file system. All right, so most of the the file system out there, they all use the journaling file system because if you're Apple, you have a working file system, so you just want to add something on top of it. All right. So that finishes this part of the file system, and we're going to go back and look at the next set of slides. All right, so we finished crash resiliencies, looking at these, few methods of how to implement it. The next one is right here. It's on. First, we're going to look at directories. Or more specifically, how do we implement the directory inode? All right? The directory inode, we sort of mentioned that before, right? It's very simple. Okay, so over here, it mentions some of the good property of the directories. One is that, you want to have the directory, inside the directory, right? Remember what's inside the directory, right? Directory is simply a mapping between a file name inside that directory, so it's a string, and an inode number. Okay, and that's all a directory is, right? It's sort of it's a list of strings and integers. Okay, the strings that we have in there, we want the string to be as long as possible. Okay, but how long can a file name be? Can it be infinitely long? That's not practical, right? You have to set a limit somewhere, but we want to be sort of flexible. We don't want to be 8.3 like in the good old DOS, have 12 characters as a file name. Okay, so we want it to be sort of reasonably long. And of course, if the file name is going to be longer than a disk block, then we say, well, forget it. Okay, so it cannot be really longer than a disk block. All right? Okay, so it needs to be reasonably long. We want the file system to be fast, and we don't want to waste too much space inside in that directory. Okay, so what does that mean for a directory to be fast? On Linux, right? If you try to do ls on /user/bin, it actually says, "Are you sure you want to do that?" Okay, because you want to show 1,000 files inside that directory. Okay, so the problem with the directory performance is that the directory can be really contain a lot of files. So that table of string, okay, as string mapped to integer, the inode number, this table can get really long. Okay, when it gets really, really long, is linear list a good way to go? No, right? If this is 1,000 entries, then whenever you need to walk down this list, it's going to take you a long time. Okay, how often do we have to do this? If you think about kernel 2, right? Kernel 2, when you try to open a file, right? Open a file slash, home slash something slash something. How many times do you perform directory lookup? Right? When you try to open a file, every time you open a file, you perform 1 directory lookup, 2 directory lookup, 3 directory lookup. You perform many, many directory lookup. Okay? If all these directories are large and you do a search, right? What you do is that you open the root, you look for the string, you go down over here, look for the string called home, and that will give you an inode number. You open the inode number, and then the inode is going to be a directory. And again, you look for a string, you look for a string, you look for a string. Okay? So if this is a linear list, it's going to perform really poorly. Okay? So it's sort of important to have the directory have a nice structure so that this operation, the lookup operation, needs to be fast. Okay? So how do we do it? Right? So again, this is what's inside a directory, simply a mapping between strings and inode number. All right, in FFS, what they did was that they tried to solve the first problem, so that the file name can be, reasonably long. And the way that they implement that is to have every entry, right? So this entry in the previous picture, okay, when they're implementing FFS, it sort of looked like this. Okay, here's one entry. Okay, over here it has the inode number in there, and also so the rest of the part is trying to store that string. Okay, and the string needs to be pretty long. So over here it tells you the first thing over here is the number of bytes inside this item. Okay, so it's the size of this this record. Okay, over here is 16 bytes. Okay, and then it tells you the length of the string length. Okay, so 4 over here is Unix is equal to 4, and then it will need to use data bytes to store the string Unix, and in FFS they also record a trailing 0. Okay, so basically this is a C string inside FFS. Okay, so over here, if you have a file name that's Unix and plus another blank character, that's equal to 5 bytes. Okay, and in I guess in FFS, the size of these records has to be a multiple of 4, so therefore you got to waste 3 bytes right here. All right, so that's why that explains all the numbers over here. Okay, the next record, this is etc., only 3 bytes plus a space that needs to be 4 bytes. So therefore, this record is 12 bytes long, and the string is 3 bytes in size. And over here, user again 3 bytes long. So if you have a directory block, okay, that block can store many, many entries over here. How do you indicate where is the last block? Okay, so over here, they're actually over here, this last block over here, if you use a large number to tell you what is the amount of free space that's left in that directory, then that will show you that this is the last entry in the directory. Okay, so actually you can use the string length and over here and this number to figure out if this thing, whether this entry is the last block or not. Okay, if this number is too high, then you know that it's the last entry. All right, and this is what is done in FFS, and it doesn't really solve the problem of what if the directory has too many entries. Okay, so again, performance is poor. All right. So FFS use order n, right? It's a linear list. Okay, so order n is linear search is no good. And again, how do you try to be more scalable? Every time you have something that's linear, it's not scalable. 2 approaches. One is to use a hash table, and the other one is to use a hierarchy. Okay, so same thing for directory data structure. We're going to look at 2 different approaches. One is to use a directory hierarchy, not a directory hierarchy, a hierarchy, and this one is called B plus trees. And B tree is something, again, that was invented by the database community, and it was borrowed from that and used it into the file system. And the other way is to implement using a hash table. Okay, we always hear that hash table. It says that it has performance of order 1. Okay, so order 1 is you got to really understand exactly how hash table is implemented to understand exactly what it means by order 1. Okay, so remember, a hash table is that you take some key, you hash it, and give you a bucket. Okay, and from the bucket, there's usually a conflict resolution chain. Okay, the conflict resolution chain, is for everything that hashes the same bucket. Okay, so certainly it doesn't really take only one operation to get to the block that you're looking for because you have to walk down the conflict resolution chain. Okay, if you're lucky, the conflict resolution chain is limited. So order one says that, well, you do one hash operation, and then you need to look for the maximum number of conflict resolution before you find the stuff that you're looking for. Okay, so the order one doesn't really mean one. It means it's some sort of a constant limited by the size of your conflict resolution chain. Okay, what if you end up with too many things that hash into the same entry? So let's say that you have a maximum number of 10, conflicting items. Okay, you have 10 already. You try to add another thing to the hash table, and now you get 11. So to violate the rule of that conflict resolution chain is 10. So the only thing that you can do at that point is to get a bigger hash table. All right, so what you do is that you take the hash table and you grow it to make it maybe twice as big, and you have to rehash everything in the hash table, and that's a very expensive operation. Okay, so the hash table are great if you don't violate any of these rules, but whenever you need to grow the hash table, and that's a major problem. Okay, in order for you to have good performance inside in your file system, as we mentioned before, that one of the important performance characteristics of a file system is that you want to minimize the number of writes to the disk. Okay, so if you have to rehash your entire directory, okay, and that will mean that you have to end up writing a lot of data onto the disk. Okay, so that's a really, really slow operation. Okay, so hash table is good, but you got to worry about what if you have to rehash into your hash table? What if you have to get a bigger hash table so you have more buckets? All right, so we're going to see how that's done in a file system. Actually, that's going to be the first thing that we will see. All right, so if you want to have a hash table, right, so what we can do is that in a directory inode, basically we're going to have pointers to different disk blocks. Okay, you're going to take the string that you're looking for, hash it, and that will tell you which block you need to go to. Okay, so in that case, if you're going to get a hit, right, then if you're going to get a hit, then the only number of disk block that you have to read is 2 disk blocks. Right, you're going to come over here to look at all the pointers, perform the hash, and then follow the pointer to another disk block. Okay, so in 2 disk read, you're going to find the file that you're looking for. Okay, the problem, of course, is the stuff that I just mentioned about, is that this disk block, it can contain about 100 to 200 entries. So if you have more than 200 things that's going to hash the same bucket, then you're in trouble. Okay, then you have to get a bigger, you're going to get a bigger inode. Can you really get a bigger inode? That's going to be sort of problematic. Okay, so the data structure that has to change. All right, so when you perform these 2 disk operations, let's say you get a hit, the stuff that you're looking for is inside this particular block. Okay, this block is going to be organized similar to the previous picture in FFS. So inside this block, you need to still do a linear search down this particular list. But over here, there's a finite number of elements that you have to do in order to find the entry that you're looking for. Okay, so therefore it's still order 1 because it's bounded by the number 200, and you only have to do 2 disk operations. Okay, so now the main problem that you have to worry about is what if you have too many entries inside your conflict resolution chain? Well, as it turns out, that the solution is that you need to have a special hash table. You need to use a special hash function. Okay, you cannot use just regular hash function that you learn in your data structure class. That's not going to work in the file system. Okay, so the one that we're going to use is something called extensible hashing. Okay, we're going to use a special hash function that has special properties. In extensible hashing, we're gonna use a family of hash functions or a sequence of hash function, and these hash functions are going to be labeled with an integer index, h0, h1, h2, etc. Okay, the index will tell you how many buckets does it have. Okay, hi hashes name into 2 to the I buckets. Okay, so h0 will give you 1 bucket, h1 will give you 2 bucket, H8 will give you 256 bucket, etc. All right, so it's progressively larger bucket. Anytime you run out of space, you get, you get a bigger number of buckets, which means that you're going to use the next level of hash functions. Okay, if currently you are in H2 and you run out of buckets, you're going to use H3. All right? Okay, so how are these hash functions related? Okay, over here it says, for any name x, the lower order I bits of hi of x are the same as hi plus 1 of x. Okay, so let's take an example. If I is equal to 2, okay, so the lower order I bits, right, that means that there are 2 bits that we're looking for. So over here, let's say that we're going to look at the lower level 2 bits. So if you take the string hello, okay, and I apply H2 to it, okay, that's going to give you 2 bits, right? So there are 4 combinations. It can maybe hash into 0, 1, 2, or 3. Okay, so over here, 0, 1, 2, or 3. Okay, so let's say that we hash hello, we're going to end up with 1, 0 right here. All right, so it's hash to the value equal to 2, and then you go over here, there's a conflict resolution chain that you look for everything that hash to 2, right? And over here, if we use H2, this conflict resolution chain, if we need to hash all the possible file name into this hash function, well, we can end up with a really, really long hash chain. Okay, so anyways, so at some point we need to use H3. Okay, so what this says is over here is that H3 of hello, okay, is guaranteed that the lower order bits of H3 has to be 1, 0. Okay, which means that when you go H3 or hello can either be 0, 1, 0 or 1, 1, 0. There are only 2 choices. Okay, if you use this extensible hash function, the relationship between H2 and H3, okay, is that the lower I bits are all the same. Okay, in this case, I is equal to 2, so the lower order I bits for H3 is guaranteed to be 1, 0 if H2 of hello hash to 1, 0. Okay, so only this, the most significant bit is going to be different. Okay, so that's why this is called extensible hashing, because H3 is an extension to H2. Okay, similarly, H4 is going to be extension to H3. So let's say that H3 or hello turns out to hash to the number 6. Okay, then H4 of hello, okay, can either be, so 110, right, can either be 0110 or 1110 equals to 6 or 14. All right, but when you hash it, it will get either one of them. You don't know which one yet, but you're going to get you're guaranteed to get either one of these 2. All right, so this is going to be the hash function that we use, right? So let's see how is that being used. Okay, in order to use this effectively, we're going to use again 1 level of indirection, okay, for this to be used in a very efficient way, right? Because the third requirement that we saw not only has to be fast, it also needs to be space efficient. Again, and also requirement for being fast is that you don't really want to rehash anything. Rehash things are slow, okay? But as you grow the hash table, well, you're going to end up, you have to rehash something. So you want to rehash as fewer things as possible. All right, so the way to do this, I'm putting them all together, is to use this indirect bucket. All right, so we're going to see this example. When we're going to hash H2, if we hash Ralph by H2, we're going to get the value 0, 0. Okay, so Ralph hashes 0, 0. If we hash Lily, we're also going to get 0, 0, right? They all go to the first entry. So 0, 1, 2, 3 are over here. Okay, if we hash Joe, it's going to be equal to 1. If we hash Belinda, it's going to be equal to 2. If we hash George, it's going to be equal to 2. If we hash Harry, it's going to be equal to 3. And we hash Betty, it's going to be equal to 3. Okay, we don't go directly into this. We're going to go over 1 level of indirect buckets. Okay, and this indirect buckets point to these records. So these records are the ones that can actually hold 100 or 200 entries. But for ease of describing this algorithm, we're going to limit that what they point to can only hold 2 entries. Okay, because otherwise our example is going to be too complicated. Okay, when they have 2, you cannot hold anymore. If you have to hold more, then we have to use the next level hash function. All right, so now our hash table is pretty full, right? Okay, we have, actually in this example, we have a possible 8 items that can be stored in our entire hash table, and now 7 items are being used. Okay, if we try to store 2 more things in them, we're going to get a new hash table. All right. So our example over here is that we'll try to insert the string or the directory, Fritz into this, or insert a new file called Fritz into this directory. Okay. Unfortunately, H2 is going to be hashed to equal to 2, right? 0, 1, 2, 3. If you follow this pointer, you will know that this particular node is full. Okay, so therefore we cannot put it in there anymore. All right, so at this point, we have to go to the next level hash function. Okay, so we have to start introducing H3. We're going to make the number of buckets from 4 to 8. Okay, so how do we do this? Okay, we increase the size of the indirect buckets. Okay, so this one used to be like this. Okay, we're going to make it twice as big. But when we make it twice as big, we're just going to copy this entire content into the second part. We're going to do a mem copy. All right, we'll copy the entire first part into the second part, which means that this entry, so 0, 1, 2, 3, 4, 5, 6, 7, number 4 is going to point to the same place as number 1. Number 5 is going to point to the same place as number 1. Number 6 is going to point to the same place as number 2. And number 7 is going to point to the same place as number 3. All right, thanks. Okay, so why do we do this? Okay, because when we do this right now, we don't have to rehash anything. All right, because right now, if we hash Ralph into H3, what are we going to get? Right, remember when we hash Ralph to H2, we get location 0. So we're guaranteed, because we're using these extensible hash functions, we're guaranteed that H3 has to be equal to 4 or 3. Okay? If H3 is equal to 4, if you follow pointer number 4, is it at the right place? All right, it's at the right place, right? Okay, if you hash Ralph by H3, if you get 0, it's also sitting at the right place. Similarly, for Joe, if you hash Joe, it can either be, right, if you hash Joe with H2, you get 1. So therefore, you're guaranteed that when you hash Joe with H3, you're only going to get either 1 or 5. Okay, if it's 1, you follow this pointer. If it's 5, you follow this pointer. So you don't have to move Joe at all. Okay, similarly, if you look at Belinda, George, Harry, and Betty, and Lily, they are all at the right place already. So therefore, when I go from H2 to H3, the only thing I have to do is that I have to get a new disk block that's a little bigger and copy the first block to the second one, and then I'm done. Okay, so this hash function is really easy to go from HI to HI plus 1. All right, so now the reason I'm doing this is because, I want to add Fritz into the directory. Okay, so what do I have to do now? Fritz is going to be we're going to hash Fritz, right? We know that when we hash Fritz to H2, you're going to get number 2. So now you're going to get either 2 or 6. Okay? And then when we hash H3, so let's say that for the sake of argument, Fritz is going to hash to hash to number 6. Okay? So if we follow the previous pointer over here, okay, number 6, if you follow this pointer, this node is full. So therefore, we have to get a new bucket. All right, so the way we're going to do this is that we're going to allocate a new node right here, number 4 right here. Okay, we're going to rehash everything in here. Okay, so Belinda and George, they're going to rehash them using H3. Some of them will go to number 2, and some of them will go to number 6. All right, so in this example, what happened is that we rehash Belinda and George. Okay, whoops, I guess that's the next page. Okay. So Belinda, turns out that it goes back to location 2, and then George go back to location 6. Right? So again, 0, 1, 2, 3, 4, 5, 6, 7. Okay, all the other guys didn't move. We just rehashed Belinda and George. Okay, so Belinda ended up to be 2, and George ended up to be number 6 right here. All right, so in this case, we'll create a new disk block, and then we copy, half of the data from here into the other part. Well, hopefully half. You can have a lousy hash function. Turns out that every one of them going to the same place. Then in that case, we have to redo it again, make it into a bigger, using a bigger hash table.
The time is
okay?
3 o'clock.
In this example, they split into two blocks, and we hash Fritz equal to 6. We follow the pointer over here. We say, hey, 6, there's room in there. We're going to put Fritz in there. All right, so in this case, when we try to insert Fritz in there, all we did was allocate a new disk block, do writes onto the disk. We're going to rewrite this to the disk and rewrite this to the disk. So 2 operations in order to fit Fritz into the hash table. All right, I guess, okay, so I'm out of time. This is a good breaking point. And next time we're going to talk about how to deal with this using a hierarchy. Okay.